Hi, welcome back to my class in differential equation. For today, we will take up another method for solving ordinary differential equation of order 1. Last time, we took up separation of variables. Today, we will take up solution of differential equation with homogeneous coefficient. Consider the following differential equation. M of xy dx plus n of xy dy equals 0. This differential equation is said to be ordinary differential equation because it contains ordinary derivative of y with respect to x. And this differential equation is said to be differential equation, ordinary differential equation of order 1 because the highest derivative that appears in this differential equation is 1. Now we say that this differential equation can be solved by the method for differential equation with homogeneous coefficients. If the coefficient of dx, m of xy, and the coefficient of dy, n of xy, are homogeneous functions of the same degree. The coefficient of dx, or differential of x, m of xy, is a function of x. Similarly, the coefficient of dy, or differential of y, n of xy, is a function of x and y. If m and n functions of x and y are homogeneous functions of the same degree, then we can solve this differential equation by the method for differential equation with homogeneous coefficients. Now, when do we say that a function is homogeneous? To define homogeneous function, we take the coefficient of the differential of x, or dx. We have the following definition. M of xy, this is the coefficient of dx, is homogeneous or homogeneous of degree k if again a function of x and y, m of xy, is homogeneous or homogeneous of degree k if m of lambda x, lambda y equals, can be written as lambda to the power k times the function m of xy, where the exponent k of lambda is the degree of homogeneity of the function m of xy. So by this definition, to determine if the given function is homogeneous of some degree k, in the given function, replace x with lambda x, replace y with lambda y, and try if you can express the resulting expression in the form as a product of lambda to the k times the given function m of xy. We take some examples. Consider the function f of xy equals x plus y all over x squared plus y squared. We will determine if this function is homogeneous. To do that, we replace the variable x. We let x equals lambda x in the given function, and we replace y in the given function with lambda y. Then f of lambda x, lambda y. F of lambda x, lambda y is equal to, replace x with lambda x, plus replace y with lambda y, all over x squared, where x is lambda x, plus y squared, replace y with lambda y. Now simplify the expression at the right hand side and see if you can write it as the product of lambda to some exponent k times the function f of xy. At the left hand side we have f of lambda x, lambda y. F of lambda x, lambda y. At the right hand side in the numerator, you can see that lambda is a common factor. Thus, we factor out lambda from the first and from the second term. And the common factor lambda multiply by the other factor, divide each term by the common factor lambda. Lambda x divided by lambda is x. Plus lambda y divided by lambda is y. In the denominator, we apply property of exponent. The square of the product lambda x is equal to the square of lambda multiplied by the square of x. Hence, lambda x squared equals lambda squared times x squared. Plus, to the second term, we again apply the property of exponent for the square of lambda y equal to the square of lambda times the square of y. Hence, the square of lambda y equals lambda squared multiplied by y squared. The numerator is the same, lambda times x plus y. In the denominator, you can see that lambda squared is a common factor. That is, the first term and the second term both contains lambda squared. So we factor out lambda squared from the first term and from the second term. And we get the other factor, lambda squared is the common factor, divide each term by lambda squared. Lambda squared, x squared, divided by lambda squared is x squared. Plus lambda squared, y squared, divided by lambda squared equals y squared. We further simplify lambda over by property of exponent. We have lambda. The exponent of lambda in the numerator is 1. In the denominator, the exponent of lambda is 2. And by property of exponent, lambda divided by lambda squared equals lambda to the power exponent of lambda in the numerator 1 minus the exponent of lambda in the denominator 2. 1 minus 2 is negative 1. Negative 1 multiplied by x plus y divided by x squared plus y squared. But this x plus y over x squared plus y squared is the given function f of xy. Thus, we can write this as lambda to the negative 1 multiplied by f of xy. Hence, we are able to write f of lambda x, lambda y as the product of lambda to some exponent multiplied by the given function f of xy. Comparing this with the definition, the exponent lambda, the exponent k of lambda is negative 1. Hence, we conclude that the given function f of xy equals x plus y over x squared plus y squared is a homogeneous function of degree -1. For our second example, consider the given function g of xy equal to sine of y over x. To determine if this function g of xy is homogeneous function, we replace x with lambda x and replace y with lambda y. And at the left hand side we have g, replace x with lambda x, replace y with lambda y. At the right hand side replace y with lambda y equals sine of lambda y over x, replace x with lambda x equals sine. You can see that here lambda y over lambda x simplifies to y over x. Because lambda and lambda will cancel out, we get y over x. And sine of y over x is the given function g of xy. But g of xy can be written as lambda to the power 0 multiplied by the function g of xy. Again, the function g of xy can be written as lambda to the power 0 multiplied by the function g of xy. Because lambda to the power 0 is 1. Hence, the coefficient 1 here of g of xy can be written as lambda to the power 0. And we have shown that g of lambda x, lambda y can be written as a product of lambda to some exponent multiplied by the given function g of xy. The exponent 0 of lambda is the exponent k of lambda in the definition of homogeneous function, which we stated earlier. Thus, the given function g of xy equals sine of y over x is a homogeneous function of degree 0. For our third example, consider the function h of xy defined by this polynomial function x cubed minus 2xy squared plus y cubed. Again, to determine if the function h of xy is homogeneous function, replace x with lambda x. And replace the variable y with lambda y. At the left hand side we have h, replace x with lambda x, replace y with lambda y. At the right hand side replace x with lambda x, y with lambda y. So the first term is lambda x cubed, lambda x to the power 3, minus 2 multiplied by x equals lambda x, multiplied by y, lambda y to the power 2, plus replace y with lambda y to the power 3. And we simplify each term by applying properties of exponents which you must have taken from your algebra course. The cube of lambda x equals lambda cube multiplied by x cube minus 2 lambda x the square of lambda y is equal to square of lambda multiplied by square of y. And the cube of lambda y equals cube of lambda multiplied by cube of y. We simplify the second term by multiplying lambda by lambda squared and applying property of exponent. The common base is lambda and we add the exponents. 1 plus 2 is 3. The first term as is lambda cube multiplied by x cube minus 2x 2 multiplied by x multiplied by y multiplied by lambda. Now we multiply lambda by y squared. Common base is y. We add the exponents. 1 here plus 2 here is 3. Plus lambda cube y cube. By inspection of the trinomial at the right hand side, the common factor is lambda cube. Each term of the trinomial has lambda cube. So we factor out the common factor lambda cube. And to get the other factor, we divide each term by the common factor lambda cube. Lambda cube x cube divided by lambda cube. Lambda cube will cancel out and you get x cube. Minus 2xy lambda cube divided by lambda cube, you get 2xy. Because lambda cube divided by lambda cube is 1, or they will cancel out. Hence, minus 2xy plus 1 lambda cube times y cube divided by lambda cube. Lambda cube will cancel out or is equal to 1. And the third term is simply y cube. But this x cube minus this trinomial x cube minus 2xy plus y cube is the given function h of xy. Therefore, h of lambda x lambda y is equal to lambda cube multiplied by this trinomial, which is equal to h of xy. And the exponent k in the definition of homogeneous function is the exponent of lambda. In this example, k is 3. Therefore, we say that the given function h of xy equals x cubed minus 2xy squared plus y cubed is a homogeneous function because h of lambda x lambda y can be written as a product of lambda raised to some exponent, which we take as k, times the given function h of xy. Hence, this function h of xy is homogeneous of degree 3. For our last example, we determine if the function g of xy equals the root of x plus y over ln of xy is homogeneous function or not. And to determine if this function g of xy is homogeneous or not, we replace x with lambda x. And we replace y with lambda y. At the left hand side, we have g of lambda x. Y is replaced with lambda y. At the right hand side, we have a square root. The root of x, replace x with lambda x. plus y, replace y with lambda y over ln of x is replaced with lambda x. Multiply by y, replace with lambda y. And we simplify this expression at the right hand side. In the radicand or in the expression inside the radical sign, we have a common factor lambda. The first term has lambda, the second term has lambda, so we factor out lambda. And we get a square root. Common factor is lambda times the other factor. We divide each term by the common factor lambda. Lambda x divided by lambda is x. Plus, divide lambda y by common factor lambda y. In the denominator, we multiply lambda and lambda. We have ln of lambda squared multiplied by xy equals, by property of radical, the square root of lambda times quantity x plus y can be written as, we can separate this as square root of lambda times the square root of x plus y. In the denominator, you can use property of natural logarithm to write this ln y squared xy as ln of lambda squared plus ln of xy. But there is no need for that because we can already see that we cannot take lambda squared out of the natural logarithm. So we simply write this as is ln of lambda squared xy. Although lambda here in the numerator has an exponent of 1/2, the square root of lambda can be written as lambda to the power 1/2. We cannot combine lambda raised to 1/2 with ln of lambda squared because lambda squared has a natural logarithm. So this function is an example of a function that is not homogeneous. This function g, defined by square root of x plus y over ln of xy, is not homogeneous because we cannot write g of lambda x, lambda y as a product of lambda raised to some exponent times this function g of xy. For your practice, please try the following exercises. Determine whether each function is a homogeneous function or not. In number 1, the given function is f of xy equals x cubed minus y cubed all over x plus y. In the second problem, the given function is g of xy equals xy times e to the power x over y. In number 3, the given function h of xy equals the square root of xy. In number 4, the function f of xy equals xy minus cosine of the product xy. For you to be able to check your answers, I have given you the degree of homogeneity for the functions that are homogeneous. For number 1, the degree of homogeneity of the function is 2, which means that the function f of xy is homogeneous of degree 2. Similarly, for number 2, the function g of xy is homogeneous of degree 2. The third function, h of xy, has a homogeneity of 1, which means that this function h of xy is a homogeneous function of degree 1. But in number 4, the function given is not homogeneous function. We now take an example of a differential equation that can be solved by the method for differential equation with homogeneous coefficients. Consider the following differential equation. Quantity x plus y dx minus x dy equals 0. Now, if you try to solve this differential equation by the method of separation of variables, you will find out that it cannot be solved by separation of variables because the sum x plus y cannot be separated. Even if you divide the whole equation by x, you will still have y over x in the sum. Now we check if this differential equation is a differential equation with homogeneous coefficients. If you compare this differential equation with this differential equation, m dx plus n dy equals 0, the coefficient m of dx and the coefficient n of dy are functions of the variables x and y. Comparing these two equations, we see that m, the coefficient of dx, is x plus y. And the coefficient n of the differential of y is negative x. We check if this differential equation is a homogeneous functions of the same degree by replacing x with lambda x and replacing y with lambda y. We replace x with lambda x. We replace y with lambda y. And lambda is a common factor. We factor out lambda. The other factor, we divide each term by lambda. By the common factor lambda, lambda x divided by lambda is x plus lambda y divided by lambda is y. And this is lambda times x plus y. X plus y is the function m, a function of x and y. Thus, we have shown that m of lambda x lambda y equals lambda raised to exponent 1. The exponent of lambda here is 1 multiplied by the function m. Therefore, the function m of xy equals x plus y is homogeneous of degree 1. Now we check if the coefficient of n, if the coefficient of dy negative x, which is equal to n, is also homogeneous of the same degree 1. In n equals negative x, we replace x with lambda x and we replace y with lambda y. Although there is no y in the function n of xy. This is equal to negative replace x with lambda x, and this negative lambda x can be written as lambda multiplied by negative x. But negative x is equal to the function n of xy. Hence, n of lambda x lambda y equals lambda. The exponent of lambda is 1. Negative x is the function n. Therefore, the function n is also homogeneous of the same degree 1. The function n is homogeneous of degree 1 because n of lambda x lambda y can be written as the product of lambda raised to some exponent k, which is 1, times the function n of xy. Therefore, the coefficients of the given differential equation, dx and dy, are both homogeneous functions of the same degree 1. Therefore, this differential equation can be solved by the method for differential equation with homogeneous coefficients. It is advisable that you note of the following when solving a differential equation with homogeneous coefficients, because this will help you out in the solution. In solving a differential equation with homogeneous coefficients, we will make use of substitution. We will introduce a third variable, and we will have a change of variable in the given differential equation. If in the given differential equation the term containing dx is simpler, then you use the substitution. Let y equals v. V now is the new variable multiplied by x. But if in the given differential equation the simpler term contains the differential of y, you make use of the substitution x equals v times y. In this given differential equation with homogeneous coefficients, the simpler term contains the differential of y. Therefore, we will let x equals vy. Again, because the term containing the differential of y is simpler, we make use of the substitution x equals vy. Now, we differentiate both sides. For the right hand side, we apply the product rule in differentiating the product v and y. At the left hand side, the derivative of x is 1 times dx. At the right hand side, we apply the product rule. We have v times derivative of y is 1 times dy, or v dy, plus y times derivative of v is 1 times dv. In the given differential equation, we replace x with vy, and we replace dx with v dy plus y dv. We have quantity x is replaced with vy plus y multiplied by dx. Dx is equal to v dy plus y dv minus x. X is vy multiplied by dy equals 0. Now, after the substitution, you simplify the given equation, simplify the resulting differential equation, and you must be able to solve it by separation of variables. After this substitution and after simplifying the equation, you should be able to solve the differential equation in simplified form by separation of variables. Here we have a common factor y, so we factor out y. And the other factor, we divide each term by y. Common factor y, vy divided by y is v, plus y divided by 1 is 1 times v dy plus y dv minus dy dy equals 0. Now you can see that the first term has y and the second term has y. So we divide the whole equation by y. If we divide this by y, divide the second term by y and the right hand side by y. Y will cancel out from the first term. Y will cancel out from the second term. And the right hand side is 0. For the first term now at the right hand side, at the left hand side is b plus 1 times b dy plus y dv minus b dy equals 0. We now distribute b plus 1 to each of these terms by distributive property of multiplication over addition. We multiply v dy by b plus 1. We have b plus 1 times v dy plus v plus 1 multiplied by y dv, b plus 1 multiplied by y dv, minus the last term minus v dy equals 0. Now we collect the terms with dy and we factor out dy. If you factor out dy from this term, you get v plus 1 times v minus v. We factor out dy, we get minus v times the common factor dy plus v plus 1 y dv equals 0. Now here we distribute v multiply b plus 1 by b, that is the right distributive property of multiplication. V times b is b squared plus v times 1 is v minus v multiplied by dy plus v plus 1 y dv equals 0. And here v minus v will cancel out. They will add up to 0. And we get v squared dy b squared dy plus b plus 1 y dv plus b plus 1 y dv equals 0. Now we can solve this by separation of variables. If we divide the whole equation by b squared to get rid of b squared from the coefficient of dy, and we also divide the whole equation by y to get rid of y from the coefficient of dv. So we divide the whole equation by yv squared. We divide b squared dy by yv squared. b squared dy we divide by yv squared plus v plus 1 y dv we divide by yv squared equals 0. In the first term, v squared will cancel out. We have dy over y. In the second term, y will cancel out. And we get v plus 1 over v squared dv equals 0. Now the first term can be integrated very easily. The integral of dy over y is ln of y. After we have separated the variables, the coefficient of dy now is a function of y. The coefficient of dv is a function of v only. And after separation of variables, we integrate both sides. The first term we integrate with respect to y. The second term we integrate with respect to v. For the second term, we divide each term of the numerator, v, and 1 by v squared. We have dy over y. Divide v by v squared plus 1 divided by v squared. dv equals 0. We have dy over y. v over v squared is 1 over v plus 1 over v multiplied by dv. We now multiply each of these two terms by dv. v over v squared is 1 over v multiplied by dv. Plus 1 over v squared by property of exponent is v to the power negative 2. That is, we bring v squared to the numerator, we take the opposite sign of the exponent of v. We get v to the negative 2 multiplied by dv equals 0. Now we are ready to integrate. We integrate the first term with respect to y, the second term with respect to v, the third term with respect to v, and we integrate as well the right hand side. The integral of dy over y, as I said earlier, is ln of y. The integral of dv over v, or integral of 1 over v with respect to v, is ln of v. And for the integral of v to the negative 2, with respect to variable v, we apply the power rule. We add 1 to negative 2. Negative 2 plus 1 is negative 1. And negative 1 we use as the divisor. Divide by negative 1 equals integral of 0 is a constant, or ln of y plus ln of v. Positive times negative is negative. Now in the final answer, we remove all the negative exponents. Hence we take this v to the negative 1 to the denominator, and we take the opposite sign of negative 1. And we get negative minus 1 over v equals c. Now we must write the final answer in terms of the original variables x and y. Hence we replace b with, at the start we let x equals b over y. And from this equation we can get v by dividing both sides by y. Divide x by y, x over y, divide dy by y, and we get v. In this last equation, we replace v with x over y, and we simplify further. To continue, we write the last equation we obtained, ln of y plus ln of v minus 1 over d equals c in terms of the original variables x and y by replacing b with x over y. We have ln of y plus ln of b x over y minus 1 over b. b is x over y equals c. We have ln y plus, by property of one of the properties of natural logarithm, ln of x over y is equal to ln of x minus ln of y. And to simplify this, we multiply 1 by the reciprocal of x over y, which is y over x, equals c. And ln y minus ln y will cancel out because they add up to 0. And we get ln of x minus y over x equals c. Now, we want to get rid of the denominator x. We multiply both sides by x. We multiply the left-hand side by x and we multiply the right-hand side by x. We have x times ln x. X multiplied by y over x. X will cancel out and you get minus y equals cx. This is the general solution of the given differential equation with homogeneous coefficients of degree 1 that we have solved by the method for solving differential equation with homogeneous coefficients. And this solution is known as the general solution because we can substitute many constants, infinitely many constants to c. Now for your practice, please try the following problem. Solve the given differential equation y dx minus x minus y dy equals 0. You try first to solve this by separation of variables. And if you cannot, you check if the coefficients of dx and dy are homogeneous functions of the same degree. If they are homogeneous functions of the same degree, then you proceed with the method for solution for differential equation with homogeneous coefficients. And for this differential equation, you take note that the simpler term contains the differential of x. That means you will, for the substitution, you will make use of y equals vx. And for you to check your answer, I give you the general solution of this differential equation. And it is y ln y plus x equals cy. In the next lesson, we will take more examples for solving differential equations with homogeneous coefficients. If you have questions about the lesson today, you ask your questions in the comments below. And don't forget to subscribe or ask your friends to subscribe to my YouTube channel, Art Kalison. Please try this problem. Thank you for being in my class today.